Hello everyone, I am Kavish Gurusingha and I'll be introducing our project SecureStay. It's cloud-native hotel booking platform and let's see what it does, how it built and the technologies behind it. This is the project overview. SecureStay is a web application where users can register, log in, search for hotels, pick a room, make a booking and pay, all in one place. What makes it interesting is that it's not built as one big application. It's broken into independent services, each with its own job, and it's designed to be secure, cloud native, and scalable. Then why microservices? Traditional applications are monolithic. Everything lives in one code base. If one thing breaks, everything goes down. With microservices, each service is completely independent. If the payment service has an issue, the rest of the service keep running. Each service can also be scaled or update on its own. That's a huge advantage. In SecureStay services, the front end is the user interface. The API gateway is the single entry point for all requests. The Auth Service handles registration and login. The booking service manages hotels and rooms. The payment service processes payment. The notification service logs events and PostgreSQL store all data one shared database across all services. This diagram shows exactly how the service connects. The browser talks to the API gateway over HTTPS. The gateway validates the JWT token, then routes the request to the right service, both booking or payment. After a booking or pay, an event is published to RabbitMQ, which is the notification service, the consume and logs. Everything flows through that one gateway. Nothing is exported directly. RabbitMQ is our message broker. Instead of services calling each other directly, which creates tightly coupled, they publish event to a queue. When a payment succeeds, the booking service publishes a message, RabbitMQ will buffer it, and notification service pick it up and process it independently. This makes the system more resilient and loosely coupled. The user experience follows 6 steps. Create an account, verify credentials, browse hotels, select dates, confirm a booking, and pay. Every step is handled by a different microservice working behind the scene. The user gets in a smooth, simple flow. The environments. First, locally on Windows using Docker Compose, fast and easy to deployment. Second, on a local Kubernetes cluster using Minikube to simulate real orchestration. And third, deploy on AWS using EKS for Kubernetes, RDS for database, and ECR for store our Docker images. We automated deployment with 2 pipelines. The infrastructure pipeline uses Terraform to provision all AWS resources, the cluster database, and networking automatically. The application pipeline builds Docker images for each service, push them to ECR, and deploy everything to Kubernetes using Helm. No manual step needs. Security was built in one user authentication with JWT token. Every request is verified at the gateway for reaching any service. Passwords are hashed using Btrip, so even if database is breached, nothing is readable. On the cloud side, we use AWS VPC networking, IAM roles, and RDS encryption to protect data and rest and the transit. So to summarize, SecureStay is a microservice-based cloud-native hotel booking platform with RabbitMQ for async messaging, JWT and Btrip for security, AWS Kubernetes for deployment, and fully automated pipelines. Thank you for listening. I'll hand over now for the technical demos. Thank you.
Recording in progress.
I am Bandara AWS Maryland under registration number PG 2021-4426. In our SecureStay project, I was responsible for deployment setup, service integration, security implementation, and end-to-end testing across all three environments: local, Docker, and Kubernetes. SecureStay is a cloud-native hotel booking system. It has multiple microservices: Auth, booking, payment, notification, and an API gateway as the single entry point. We use PostgreSQL for booking and payments, MongoDB for notification logs, and RabbitMQ for async event messaging between services. All 5 services that I mentioned earlier are running locally. Gateway on port 4000, Auth on 4001, booking on 4002, payment on 4003, and notification on 4004. All are healthy. Register a new user through the API gateway. The password is hashed with bcrypt. Raw passwords are never stored. The user gets a UUID and a customer role by default. Login returns a JWT token signed with HS256. The token contains the user ID, email, and role. It expires in 1 hour. This token is required for all project protected routes. Without it, you get 401. Hotel search is a public endpoint. No token needed. The data comes from our PostgreSQL seed data. We then get the rooms for a specific hotel, which shows the room type, price per night, and capacity. Creating a booking requires a valid JWT token. This is protected by our Auth middleware. The booking starts with pending status. The system automatically calculates the total amount based on nights multiplied by price. A booking.created event is also published to RabbitMQ at this point. Payment succeeds with status success. Notice the mask card number. Only the last 4 digits are stored. Raw card data is never persisted in our database. The booking status automatically updates from pending to confirmed. A payment.process event is also published to RabbitMQ. The notification service receives both events to RabbitMQ, booking.create and payment.processed. This is asynchronous communication. The booking and payment services did not wait for notification processing. They published events and continued. The notification service consumed them independently and saved them to MongoDB. I created multiple bookings, so we can see booking.created in here and in here. So multiple booking created events are here, and it's also here also, and then only one payment is done. So we can see only one payment process event in here. Payment process event is here. In the card also, only the last 4 digits are stored, others are in star marks. Which is more invalid token. So, without a token, protected routes return 401 immediately. That means missing or invalid token. Internal service routes are also blocked at the gateway level. External users cannot access service-to-service endpoints. We also have role-based access control where admin users can view any booking, but customers can only see their own records. In the gateway service, we can see that our gateways and also in the notification service, you can see booking created events and payment processed events. In Docker mode, we have to stop the local services and start the Docker containers. So I start them. Notification service, gateways, Frontend, and all other things are done. In Docker mode, all 9 containers run together. 5 services, 2 databases, RabbitMQ, and the frontend. A single Docker compose up command starts everything. So we can see all the things. Gateway service is gateway, status is okay, Docker 4000. Health checks in Docker Compose ensure services only start after their dependencies are ready. The same API works identically inside containers. Before moving to Kubernetes parts, I have to stop the Docker related things and then start the Minikube for Minikube parts. Then I ran Kubernetes get pods to check whether the services are running or not. So here we can see all 5 services and Postgres, RabbitMQ, and Frontend is running here. I will run commands and then explain later Kubernetes get pods and then Kubernetes get services, all the services we see, and secure health check. In Kubernetes, Auth and booking services run with 2 replicas, each for high availability. All pods have readiness and liveness probes using the health endpoint. So, traffic only goes to healthy pods. If a pod crashes, Kubernetes automatically restarts it. Credentials are stored in Kubernetes secrets. Nothing is hard-coded. The gateway is exposed via Node port for external access. That covers my contribution to SecureStay. Deployment across all three environments, JWT security with role-based access control, end-to-end integration of all 5 microservices, and asynchronous event flow through RabbitMQ. Thank you.
Now I will explain AWS cloud infrastructure of our project. Here, users first open the hotel booking application using website URL. Their request first goes to the AWS load balancer through the net gateway, and the load balancer helps to traffic and prevents one server from getting overloaded, and the whole system runs inside the virtual private cloud. That means private cloud network. The VPC is divided into the public and private subnets across 2 availability zones. This helps to improve security and availability. Inside AWS EKS cluster, which is Kubernetes on AWS, our applications are running. These services include the Frontend and API gateway, Auth Service, booking service, payment service, and notification service. Kubernetes manages these services using pods and automatically restart them if something fails. It can also scale the application by creating more pods when traffic increases. The ingress component routes request to the correct service based on URL path. The application uses Amazon RDS PostgreSQL as the database. The database is placed private subnet, so it's not directly accessible from the internet. RabbitMQ is used for communication between services. For example, after booking is completed, RabbitMQ helps send notification without slowing down the main application. Docker images of all services are stored in Amazon ECR, that means Elastic Container Registry. GitHub Action is used CI/CD pipeline to automatically build and deploy the application to Kubernetes whenever the code is updated. For security, we use IAM roles and security groups and encrypted communication. Overall, this architecture helps to system become scalable and secure and highly available. Next, you can see the proof of the deployment. This is the public cloud hosted version of the SecureStay. A user can open this in a browser, register and log in, view hotels and create booking and make a payment. So this is proves that the system is not only deployed but also usable from the cloud. In the right hand side, you can see the terminal. Here we can confirm that the Kubernetes cluster is running in AWS. We can see the nodes, application ports and the services. The front-end services exposed through a load balancer, so users can access application through the public URL. Now I will mention challenges briefly. Moving to the cloud also created some challenges. AWS infrastructure is more complex than local deployment. We had to configure IAM, VPC networking, security groups, ingress and port capacity and database connections correctly. We also faced so many issues, such as load balancer delays, port scheduling limits and database secret configuration. But solving these issues helped us understand real-world cloud deployment much better. Then finish with this handoff. So overall, AWS gave us more secure and production-like environment for SecureStay. Terraform help us create the infrastructure in a repeatable way, and EKS help us run the application reliably in Kubernetes. Now, Diane will explain how we automate this infrastructure and application deployment using GitHub Actions pipeline.
Next, before showing the workflows, I'll briefly introduce the two deployment pipelines used in project. Pipeline is an automated sequence of steps that builds, provisions, and deploys systems consistently without manual intervention. So in this project, two main pipelines are used, the infrastructure pipeline and the application pipeline. So infrastructure pipeline is responsible for creating and updating the cloud foundation using Terraform. It starts by checking out the infrastructure code, then securely connects to AWS using credentials. Next, Terraform init prepares the Terraform environment. Terraform validate checks the configuration, and Terraform plan previews what changes will be made. So after manual approval, Terraform apply provisions or updates AWS resources such as the VPS, subnets, EKS, cluster, those things, and security groups. So finally, outputs such as RDS endpoint and EKS cluster details are generated. So this makes infrastructure repeatable, scalable, and easy to recreate. In the second workflow is the application pipeline, which builds and deploy application to EKS. It starts with the prepare stage to create a release image tag, then build creates Docker images for all services. Those images are pushed to Amazon ECR, Kubernetes secrets are created, and pre-flight checks verify pod capacity readiness before deployment. Next, Helm deploy services to EKS, verify checks rollout status and service endpoints, and rollback provides recovery if deployment fails. Together, these two pipelines automate both infrastructure provisioning and application deployment in secure and cloud native way.
Okay, this part demonstrates the CI/CD pipeline and automated cloud infrastructure deployment using GitHub Actions, Terraform, AWS, and Kubernetes. Instead of manually configuring resources, the entire deployment process is automated through pipelines. When code is committed and pushed to GitHub, it automatically triggers the CI/CD workflow to build, validate, and deploy the application. Now here we can see after executing git push, the pipeline will start to run in GitHub. Now we can see our pipeline is running in the GitHub. Here it starts by preparing release metadata, then builds and pushes containers, images for the front-end, API gateway, authentication, booking, payment, and notification service. After that, the services are deployed to Amazon EKS using Helm. This makes application deployment fully automated, and still the pipeline is running. We can see there's no error, still it's running. It takes few minutes. Okay, here we can see it's complete each step, and now we can see the pipeline has completed successfully. Next is a Terraform apply pipeline, which provisions cloud infrastructure automatically using infrastructure as code. It configures AWS credentials, setups Terraform, Helm, and Kubernetes. then initialize and applies the infrastructure configuration. These provisions resources such as EKS, RDS, ECR, networking, and load balancing. It then verifies the Kubernetes cluster, and now we can see that pipeline also is running. These are the main stages, including configure engine X ingress and output deployment details like the load balancer, hostname, and database endpoint. These are the main stages of Terraform deployment workflow, and still the workflow is running. We can see now the pipeline has completed successfully, and together these pipelines demonstrate automate deployment, infrastructure as code, scalability, high availability, and secure cloud native deployment practices.